In this video, we're going to take a quick look at magnetic dipoles, focusing mostly on the main results, not going through all of the derivation, and we're going to compare the results to what we saw for our electric dipoles in a previous unit. And so it turns out we have two different ways that we can create magnetic dipoles. The first is a bar magnet, and the second is a small current carrying loop. And so, of course, our bar magnet is a little more obviously analogous to our electric dipole that we considered previously. So just as a very brief refresher, remember our electric dipole, we had some charge positive Q, so Q plus, and some charge Q minus, which were separated by some small distance d. And so, of course, if we consider some small bar magnet with a north and south pole, that's pretty clearly a good analogy. But how exactly does our small current carrying loop create the same type of conditions as either of these two structures? So in order to answer that, let's take a closer look at our small current carrying loop. So I've drawn here some small loop with current I, which is centered at the origin and it's in the xy plane. So this is at the z equals 0 plane. And so let's say we have some point of observation P, and so I've defined this point in spherical coordinates, so we have r, theta, and phi. So of course our r is going to be the radial distance from the origin, our theta is this angle coming down from our z-axis, so that's going to be our theta, and our phi is going to be the angle coming over from our x-axis. And so notice I've got sort of these dashed lines indicating that this is in our positive x, positive y, positive z octant. So if we were interested in our magnetic field, how would we go about finding that? So first what we would do is we would define some differential length of this path, and we would say that it has a differential current I times dl, and so let's just focus on that differential length dl. And so what we could do is we could start by finding our magnetic vector potential. So let's look at our magnetic vector potential. And so we didn't look at this equation specifically in the notes, but we kind of alluded to the fact that we could find our magnetic vector potential directly from the current. And so if you look back on page 320 in the text, you'll see where this equation comes from. But we can directly get this magnetic vector potential A from our current. And if we have a line current, we can say that's equal to mu naught times the current in that line divided by 4 pi, integral over the closed loop of dl divided by the distance r, where r is just the distance from our sort of the center of our loop to our observation point P in this case. And so again, we're not going to go through all of the analysis of this, but what we would see is if we're considering the case of the far field, so for far field, which is just defined as our r being much greater than a, so we're really, really far away compared to the radius a, so I forgot to point that out, but we have some radius a of this loop. So if our point of observation is very far away compared to the sides of the loop, what we can show is that ultimately we get our magnetic vector potential A becomes mu naught times I pi a squared sine of theta divided by 4 pi r squared, and that's going to be in our phi direction. Okay, so let's point out a couple things here. So we notice that this pi a squared term is actually just the area of our loop. And so what we can do, see if I can write a proper P first of all. There we go, so that's the area of our loop. So what we can do is we can rewrite this A equation in terms of our magnetic dipole moment. So you might have been wondering when we were talking about torque, why do we call that our magnetic dipole moment as opposed to just our magnetic moment? And so that's because we can relate it to this dipole action of our small current carrying loop. So we can say this is mu naught times our magnetic dipole moment cross with a unit vector in the r direction divided by 4 pi r squared. And so the reason we can say that is, recall in this case Rm is going to be along u of z from our right hand rule. So Rm is going to be along u of z from our right hand rule. And so of course we could slightly adjust this equation if we have a different position or different orientation. We just need to change a couple things in terms of our directions and our distances. Okay, so that's our magnetic vector potential, but ultimately, we're usually going to be interested in our magnetic field or our magnetic flux density. So of course we know how to get our magnetic flux density fairly easily from that. So our magnetic flux density can be found just from saying RB is equal to del cross A, so the curl of our magnetic vector potential. And so again, we're not going to go through all the steps of that. However, if we do that, we find that our magnetic flux density is equal to mu naught times m, so just the magnitude of that magnetic dipole moment, divided by 4 pi r cubed, and all of that is multiplied by this quantity, so we have 2 cosine theta in our r direction plus sine of theta in our theta direction. Okay, so that is the end result for the magnetic flux density due to this small current carrying loop centered on the origin in the z equals 0 plane. And again, we can adjust that by defining all of these vector directions locally if we have a slightly different position or orientation of our current carrying loop. Okay, so let's then compare to our E expression for a dipole, for an electric dipole. So compare to E for an electric dipole. And so we saw this previously in the notes. If you go back to page 152 in the text, you can see this equation here, but basically we found that our electric field due to a electric dipole is equal to QD divided by 4 pi epsilon naught r cubed times 2 cosine theta in our r direction plus sine theta in our theta direction. And so just as a refresher, this QD in the numerator up here was our dipole moment, or the magnitude of our dipole moment rather, and this was just previously defined as P. And so of course what we can see is that these two equations here have a very similar form. So this factor out front is slightly different. We have our epsilon naught in the denominator versus our mu naught in the numerator. But other than that, the equations are essentially identical. So that's how we can say that our small current carrying loop is behaving like a magnetic dipole. So because of this similarity, our small current carrying loop is a magnetic dipole. Okay, so now let's briefly talk about our bar magnet as well. So if we have some bar magnet, so bar magnet with some length L, and let's say we have isolated magnetic pole or charge strength, so magnetic charge slash pole strength Q sub m. And so remember, we can't actually create a magnetic monopole, so that has to be accompanied by some, so let's say we have to accompany this with some minus Qm. And so unlike with our electric dipole, we can never just have one of those, we have to have both. That's going to result in some dipole moment, which is just going to be Qm times L. So dipole moment Qm times L, where our L is going to be from south to north, from our south pole to our north pole. So if we had something like this, if this is our electric dipole, we're saying we have some north pole, which has some equally strong south pole associated with it. Our L is going to be in this direction here, and we could also talk about magnetic flux lines. So let's briefly show those. So magnetic flux lines, and so this is also just going to kind of drive home the similarity between our magnetic dipoles and our electric dipoles. So we have these magnetic flux lines which are going to be originating at our north pole and moving towards our south pole and terminating at the south pole. Of course, we also have these flux lines sort of continuing inside of our bar magnet as well. And so we can draw more flux lines. So we have something that looks like this maybe. And so we can draw any number of these. So these should be sort of symmetrical. So I'm not doing a great job of drawing it, but we have something like that. And so this will come back and come in here and something like that. And so again, that direction is they're always originating at our North Pole and terminating at our South Pole. And so what we can do is we notice that that's actually very similar to the flux lines, the electric flux lines that we saw for our electric dipole. So if you look on, again, page 152 in the textbook, you can see the electric flux lines for our electric dipole. And we can also look at the magnetic flux lines for our small current carrying loop. And so if you look on page 365 of the textbook, you can see that the magnetic flux lines for that small current carrying loop, as we would expect, look the same as what we see here for this bar magnet.